In today's video, we are going to explore how objects interact with electromagnetic radiation and how this interaction affects their temperature. Whether we consider something as common as a cup of tea or something as simple as an ice cube, every object is continuously absorbing and emitting electromagnetic radiation in exchange with its surroundings. This exchange plays a crucial role in thermal energy transfer. When an object absorbs radiation, it takes in pure energy, and as a result, it warms up. On the other hand, when it emits radiation, it loses energy and consequently cools down. The temperature of an object is therefore influenced by the balance between the energy it absorbs and the energy it emits. For example, if we take a hot object like a cup of tea that is warmer than the surrounding air, it will emit more radiation than it absorbs, leading to a gradual loss of energy and a decrease in temperature. In contrast, a cold object like an ice cube, which is cooler than the surroundings, will absorb more radiation than it emits, causing it to gradually warm up over time. However, if an object reaches a point where the energy it absorbs is equal to the energy it emits, it will maintain a stable temperature because it is neither gaining nor losing heat energy overall. To delve deeper into this concept, we need to understand that electromagnetic radiation exists in a spectrum composed of many types, ranging from ultraviolet and visible light to infrared radiation, each with its own unique properties. One key idea in this topic is intensity, which refers to the amount of energy that is transferred per unit area in a given amount of time. In simple terms, intensity measures the power of the radiation in a specific area. We can represent this concept visually using a graph that shows the relationship between the wavelength of emitted radiation and its intensity. On this graph, the horizontal axis represents the wavelength of the radiation, while the vertical axis represents the intensity. This kind of graph helps us understand how much of each wavelength is emitted by an object. A higher intensity on the graph means more of that specific wavelength is being emitted. For practical purposes, we focus mainly on ultraviolet radiation, visible light, and infrared radiation, which are arranged from left to right on the wavelength axis because they increase in wavelength in that order. If we take an object at room temperature, such as a paper bag, and plot its emitted radiation, we would see a curve that peaks in the infrared region. This tells us that most of the radiation emitted by cooler objects is infrared and that overall, they emit relatively low amounts of energy. Now, if we consider a much hotter object, like a glowing piece of burning coal, the curve shifts upwards and towards the left, indicating two things. It emits more energy overall and the peak emission moves towards shorter wavelengths. The same principle applies even more strongly to an object like the sun, which is incredibly hot. Its emission curve shifts even further to the left and higher up, showing intense radiation in shorter wavelengths like visible light and ultraviolet. From this, we learn that as an object's temperature increases, the intensity of all the emitted wavelengths increases too. However, the rise in intensity is not equal across all wavelengths. The intensity of shorter wavelengths increases more rapidly than that of longer wavelengths, which causes the peak of the emission to shift toward the left on the graph. This explains why hotter flames, like those from a Bunsen burner, change color as they get hotter. A cooler flame emits longer wavelengths and appears reddish-orange, whereas a hotter flame emits shorter wavelengths and appears blue. For most everyday objects at room temperature, all the radiation they emit falls within the infrared region of the spectrum, which is why we cannot see it with the naked eye. Our eyes are only sensitive to visible wavelengths, so the radiation from room temperature objects remains invisible to us. The final concept we need to discuss is that this balance of absorbed and emitted radiation does not only apply to small objects, it applies on a planetary scale as well. Our entire planet, Earth, is constantly absorbing electromagnetic radiation from the sun, primarily in the form of visible light and ultraviolet rays. At the same time, the Earth emits its own radiation, predominantly in the form of infrared waves, because it acts like a large warm body in space. The Earth is also surrounded by an atmosphere, which complicates this energy exchange further by reflecting, absorbing, and emitting radiation itself. During the daytime, the Earth and its atmosphere absorb more energy from the sun than they emit, leading to an increase in local temperatures. At night, the process is reversed, less energy is absorbed and more is emitted, so the local temperature drops. However, since different parts of the Earth are always exposed to sunlight at any given time, there is a balance on a global scale that keeps the overall temperature of the planet relatively constant. Anyway, that concludes everything for this video. Hopefully all of the explanations help to clarify how radiation affects temperature and how this principle applies both to individual objects and to our entire planet. If you found this helpful, please consider giving us a like and subscribing to the channel, and we will see you again very soon.